Hi, my name is Layla Puglisi, and my Physics of Blank project is Physics of Archery. It started back in 2018 when my dad gave me, or actually made me cry because I couldn't hold his 10-pound bow, and he called me weak. Then after that, he actually helped me learn more about archery, and I found that I was very passionate about it. And so here I am talking about it because it's something that makes me happy, and I'm actually really intrigued by its physics. So the first topic I want to talk about is projectile motion as well as forces. Projectile motion is a direct derivative from Newton's 3 laws of motion, specifically his second law. The sum of the forces acting on the object is equal to the object mass multiplied by its acceleration. Once the arrow is released from its original resting place on the bow, the string proceeds to bounce back and forth, as well as the arrow continues to wiggle side to side until it stops at its designated target. Or you could completely miss it, as shown here.
Perfect!
When the arrow is fully drawn back, the force of the arrow is equal to the force applied by the archer. Because of Newton's second law and the equation sigma F equals ma, you could calculate the physics applied during the drawing and immediate release of the arrow. Because the arrow is moving forward at a high speed while simultaneously falling towards the earth thanks to gravity, its path is actually a parabolic curve. To hit the target at a distance the archer cannot aim directly at the center or perfectly in a straight line. Instead, an archer must aim the arrow slightly towards the upward angle. The arrow climbs to a peak height, its apex, you could call it, and then arcs back down, and it ideally, in a good scenario, hits a bullseye. Here is a video of both me and my dad shooting our bows. A key thing to note when watching the video is that even when me and my father release the arrow from our bow, our arms stay up and we don't let the bow fall to our side immediately. This is because we do not want the arrow to change trajectory, because that is something that does happen. It's part of the archer's paradox, which is the next thing we want to learn. My second topic that I would like to bring up is aerodynamics as well as the archer's paradox. But before that...
Trivia! First question.
The only question.
An arrow is launched horizontally from a height h above flat ground with an initial speed v0. Assuming air resistance is negligible, which of the following expressions correctly represents the time t the arrow remains in the air? A, t equals square root of 2h over g. B, t equals v0 over g. C, t equals square root h over 2g. D, t equals 2h over v0.
See?
Wrong.
Ah! Wait, can I guess? Okay. I'm wrong. I'm getting tilted, though. B?
Wrong.
Oh! You're 50-50 now. I don't like this. Come in camera. Sorry. A.
Correct.
Ah! Okay. You're safe. Can we not go into Come on. Behind me. No, soft, bro, soft. Please.
Don't draw hard.
I won't.
No, please. Yo, you can cover your face.
You can cover your. Oh,
you
lucky.
missed.
Oh my god.
Are they not popping? I think he has to go harder for it to pop.
Yeah, I have to go harder for it to pop.
Are you my dad doing it?
No.
Do it on your back.
Watch this.
Oh no. Oh my god. No, that doesn't count, guys. Are you gonna pop it on my back? No, you dare.
He's gonna pop it above your head.
Back to the topic at hand, aerodynamics causes a constant bending which overall fluctuates areas of high and low pressure on alternate sides of the arrow shaft, leading to quick destabilism within flight. Another important factor about aerodynamics would be fletching, as well as the drag. Fletching are the feathers found on the back of the arrow, as well as the tiny little veins that are carved. As for the drag, it is caused when the arrow wiggles within the air and air passes through those little veins, catching it and helping the arrow with a smooth passage towards the target. The archer's paradox is a phenomenon where the arrow must be aimed slightly away from the target, yet it flies straight and hits head-on, creating a bullseye. It's first due to the bend of the arrow from the bow riser, then it swings back towards the bow's riser, and it ultimately creates a wag in the arrow's tail.